So today we're getting into chapter 7, which is on exponential functions. And so first of all, let's go ahead and define what an exponential function is, and then you're actually going to graph exponential functions. And so that's what we're going to be using the netbooks for. And so first of all, a parent function of exponential growth functions basically states if you have f of x equals b to the x, where b is any number bigger than 1. So 2 to the x, 3 to the x, something like that. This is what your graph is going to look like. It is going to get small and then get bigger. Okay, the graph will be continuous. What does continuous mean? Continuous. When I say it's non-stopping, it never ends. The thing with continuous is that there are no breaks in the graph. That means if you were to walk along this, you will never fall off. 1 to 1 means for every x value, there is exactly one y value. Increasing means that it increases, it gets bigger. Okay, the domain of this is all real numbers. Okay, the range, on the other hand, is not all real numbers, because what can you tell me about the range of this? Because remember, the range is the y's. It's positive reals. Basically, when you think about the range, it's all the y values above 0. Okay, so another way of saying all positive real numbers is to say y is bigger than 0. Okay, when it says an asymptote, the x-axis, have we talked about asymptotes before? An asymptote is like an invisible boundary. When you think about an asymptote, you think about an electric fence. You don't ever want to touch it, because if you do, you'll get zapped. Okay, so the x-axis here is an electric fence. The graph will never, ever touch it. It's going to get close, but it will never, ever touch it. Okay, and so we usually represent asymptotes with the dashed line. And then the y-intercept, since it doesn't touch the x-axis, it will never have an x-intercept. The y-intercept, on the other hand, is at 0, 1. So what I need you to do now is we're going to go ahead and graph y equals 3 to the x. And so we need to go to our site that we graph in. So if you want to go ahead and go to the rentcalculators.org, okay, go ahead and go to the site rentcalculators.org, which is where we've been before. Remember to select the free online calculator on the left side. And once you select that, select the free online graphing calculator. Okay, so rentcalculators.org, the free online graphing calculator, and then you should get this. Okay, now if you want to make it bigger, you can. Now we're graphing y equals 3 to the x. So we need to start with the 3, a caret, and then the x. Okay, so go ahead and graph that. And when you graph that, you're going to have to make some observations. So I want you to think about, when you click graph here, that looks real similar to the other one, right? What? You'll have to go get another one. Okay, so go ahead, and what do you notice about that graph?
It's touching.
It's what?
It looks like it's touching the X. I mean, everything.
I was doing this one for Drew. Okay, so the graph looks real similar to the other one, right? But we need to kind of be aware of what this looks like. And this looks really similar to the first one. So let's talk about this. First of all, it's continuous. It's 1 to 1. It's increasing. Has a y-intercept of what? 1. Okay, the x-axis, once again, is an asymptote, and that's one of those things that you just kind of have to be aware of. You kind of just have to know that when we graph one in this form, you've got an asymptote. What about the domain? What can you tell me about the domain? It's going to be all reals. What about the range? The positive reals. So what's another way we could write that? So first of all, I know the domain is all reals. What's the range going to be then? All Yeah, all positive reals. How about we do this? All reals greater than 0. Because we've done that before, remember? We would write it as y is greater than 0. So that would be another option. You could do that or you could do this. That's it. So far, so good? Let's look at another one then. This is what I need you to do now. Be really careful how you enter this in. You're going to go 2 to the x, and then you're going to put plus 1. Okay, so let's go ahead and go into the 2 to the x, and then plus 1. I'm going to change mine to pink. Now, once you get that graph, you should go ahead and look at what I have up here on the screen, because that's exactly what you should have. You should have the exact same thing. So what do you notice about this graph versus all the other ones? It doesn't touch the x-axis, but it looks like the graph has been shifted, right? What direction? Up. So it looks like it's been shifted up. What can you guess it's been shifted up? How many? Why 1? Because it says plus 1. If you look back at the original problem says plus 1. So then when we look at the visual and we're like, hey, that's been shifted up, it looks like it's 1. Well, that's why it's 1. So if this would have been plus 2, it would have shifted up how much? 2. See how that works? If it would have been 5, it would have been shifted up 5. So it's whatever that number is, and that's going to tell you what it shifts. So what is that going to change when I'm factoring in my domain and range? What's my domain going to be? My domain's going to be what? All reals again. What's my range going to be? All reals greater than 1. So that's what it's going to affect. It's going to affect your range because it's no longer going to be going down that low. Questions? Okay, so let's go ahead and see what we have here. Ooh, that's a good one. 0.1 times 6 to the x minus 3. So before you even graph this, I want you to tell me, what do you think this graph is going to do from the original ones we looked at? Down what? 3. Okay, let's see if it works. So 0.1 times 6 to the x minus 3.
Exactly how it is shown.
So 0.1 times, there you go. Notice how I did that. 0.1 times 6 to the x, yes, minus 3. Now, you think it's going to be shifted down 3. Let's see. Yeah. Ooh, yep. There you go. Good call. Good call. Now, it looks like it actually touches the 3, but it really doesn't. What affects this problem is that 0.1, because what that 0.1 does is it shrinks it down so it's so that's why it looks like it actually touches it. But if you look at the table over here on the right side, okay, you're getting awfully close to -3. So let's go ahead and find our domain and range. What's our domain going to be here? All reals. What's your range going to be?
All reals greater than -3.
All reals greater than -3. Now, you're probably wondering, why are we even looking at things like this? Exponential functions are used a lot. They're used a lot in nuclear physics. They're used a lot in exponential growth and decay. They're used a lot in money. Financial institutions use exponential growth and decay that deals with like finances, things like that. So anyway, what you need to do for me, and that's why I'm going to give you time to work now, because you are going to need the netbooks. I need you to do page 456, 13 through 19. Now, we need to go ahead and, let's go ahead and look at those to make sure that we're on the same page as to what you're going to be doing. Okay. You need to graph each function and then state the domain and the range. So I need a snapshot of what your graph looks like. I need you to write that down on your paper tell me what the domain and the range is, and that's it.